नमस्ते बच्चों, वेलकम। आज हम यूनिट 7 का एक बहुत ही इंपॉर्टेंट टॉपिक पढ़ने वाले हैं, द सीरीज LCR सर्किट। एंड आई प्रॉमिस यू बाय द एंड ऑफ दिस आई विल मेक इट सो सिंपल कि आपको लाइफ लॉन्ग याद रहेगा एंड इट विल बी परफेक्टली सेफ फॉर योर एग्जाम्स। चलो शुरू करते हैं।
Have you ever thought about this? When you turn that knob on your radio, how does it magically catch just one station, say 98.3 FM, and completely ignore the hundreds of other signals that are floating in the air? Well, the secret behind this everyday magic is the LCR circuit, and today we're going to unlock it together.
So, first things first, let's understand the problem we are facing. Just imagine we have a team of 3 components connected in a line, in series. There's a resistor, an inductor, and a capacitor. Now, the problem is they all behave very, very differently when AC current passes through them. It's like a team challenge.
So, let's meet our 3 players. First up, we have the resistor. He's a simple, straightforward teammate. His voltage walks perfectly in step with the current. Then comes the inductor, who's like the team leader. Its voltage is always 90 degrees ahead of the current. And finally, the capacitor, who's a bit lazy. Its voltage always lags behind the current by 90 degrees. Now just think, when the same current flows through all 3, their voltages are all pulling in different directions. This is their tug of war that we need to solve.
So how are we going to solve this voltage tug of war? For this, we are going to use our master tool, the phasor diagram. Now, phasors are basically just rotating vectors that help us visualize AC quantities. Let's see how this diagram builds our understanding and helps us find the winner of this tug of war. The first rule for drawing any phasor diagram for a series circuit is to decide on reference. Now, since the current is the one thing that's the same for all 3 components, it makes sense to make the current phasor our constant reference point. We'll just draw it horizontally.
Okay, have a look here. We draw the current phasor, I, horizontally. Simple. Now, what about the resistor's voltage, VR? Well, we know it's always in phase with the current, so its phasor lies right on top of the current phasor, pointing in the exact same direction. Easy enough. And now for the interesting part. The inductor's voltage, VL, leads the current by 90 degrees, so where does its phasor point? Straight up. And the capacitor's voltage, VC, lags the current by 90 degrees, so its phasor points straight down. See? Now we have a clear tug of war happening in the vertical direction.
And this builds up to our famous impedance triangle. Look, to find the total voltage, we first find the result of the vertical tug of war, which is simply VL minus VC. Then we combine this result with the horizontal voltage VR using Pythagoras' theorem. Now, if we just divide all these voltages by the current I, we get a triangle of opposition. Its base is the resistance R, its vertical side is the net reactance, that is XL minus XC, and the hypotenuse is Z, the total opposition.
This total opposition, it has a special name, impedance, represented by the letter Z. It's the overall effective resistance of the entire AC circuit. And as you can see from our triangle, its formula is Z equals the square root of R squared plus the square of XL minus XC. This formula beautifully combines the resistor's simple friction with the net result of that inductor-capacitor tug of war.
Chalo, now let's get to the most important part of this topic. What happens at one special, one magic frequency? This is really the heart of the LCR circuit.
Let's ask a very important question. Look back at our tug of war. What would happen if the inductor's upward pull, its reactance X sub L, becomes exactly equal to the capacitor's downward pull, its reactance X sub C? What if they perfectly cancel each other out? This single question, this leads us to the most important concept in this topic, resonance.
Now, pay close attention to this slide. It shows the 3 different personalities of the circuit. If XL is greater than XC, the inductor wins, and we call the circuit inductive. If XC is greater, the capacitor wins, and the circuit becomes capacitive. But in that one special case, when XL becomes equal to XC, the 2 reactances completely cancel each other out, and the circuit becomes purely resistive, where voltage and current get back in a straight line, just like old friends.
This special frequency where this magic happens, where XL equals XC, this is called the resonant frequency. Its formula, omega naught equals 1 over the square root of LC, depends only on the values of the inductor and the capacitor. Beta, this formula is extremely important for your exams. You have to remember it.
So let's just think for a moment. At this magic frequency, the 2 opposing reactive forces, the up and down pole, they completely disappear. The term XL minus XC becomes 0. So what happens to the total opposition, the impedance Z? It drops down to its absolute minimum possible value. The impedance Z simply becomes equal to the resistance R.
And according to Ohm's law, if the total opposition is at its lowest, what will happen to the current? Exactly. The current will surge to its highest possible value. And Bacho, this is exactly how a radio works. When you tune your radio, you are actually changing the value of C until the resonant frequency of your circuit matches the station's frequency. At that exact point, impedance is minimum. The current from that one station becomes maximum, and you can hear the song perfectly clearly.
Okay, now for some very important points that can save you precious marks in your board exams. Let's look at some common traps and misconceptions.
Please pay close attention here. These are the silent killers in exams. First mistake. Students think that at resonance, the resistance becomes zero. No, absolutely not. Only the net reactance becomes zero. The friction from the resistor is always there. Second mistake. Students believe the voltage across L and C becomes zero. Again, wrong. Their voltages are equal and opposite, so their vector sum is zero. But individually, VL and VC can be very, very large.
To avoid that first mistake, just remember this one line. At resonance, the path becomes clear of the up and down obstacles created by the inductor and capacitor, but the friction of the road, the resistance, it always remains.
So chalo, for a quick revision, let's summarize the whole topic. These 5 points must be on your fingertips. First, in a series LCR circuit, current is the constant king. Second, impedance Z is the total opposition, which we find using vector addition. Third, resonance is that special condition when XL equals XC. Fourth, at resonance, impedance is minimum and current is maximum. And fifth, at resonance, the circuit behaves just like a simple resistor. Please remember these 5 points well.
And you know, this phase relationship, that small angle phi in our impedance triangle, it's not just for LCR circuits. It's the foundation for our very next topic, power and power factor in AC circuits. We will see how that little angle decides how much useful work we can get from our circuit. So be ready for that.